Okay, so this is the final video in this topic of uncertainties and errors. And what I'm going to teach you now is how to determine final uncertainties and stated results, where you actually have to do calculations with experimental data. And this is obviously really, really important. Okay, so you've seen the poster in the front of the room. Okay, I'm just going to go over these. If data are added or subtracted, what you do is you add the absolute uncertainty. So very easy, okay? This is the simplest case. If data are multiplied or divided, what you need to do is add the percentage uncertainty. And typically what we do is we express everything in its final form as an absolute with an absolute uncertainty. So what you'll have to do with multiplication and division of experimental data is you'll have to kind of toggle between percent uncertainties and absolute uncertainties. After you do it for a while, it will become so automatic to you that you won't even have to really think about it. And we'll do lots of examples, but study the way I have it stated mathematically here and make sure that you understand this, okay? How this mathematically, all this gibberish here is actually a mathematical statement of this English sentence up above, okay? If data are raised to a power, you multiply the percent uncertainty by that power. And again, make sure that you understand this mathematical statement of that English sentence, okay? So generally, like I said, you want to leave all your final calculated answers with an absolute uncertainty. It's really not very good form to leave your final answers as a percent uncertainty. You can, but generally it's easier to understand what's happening if you report it with an absolute uncertainty. So as an example, spend some time, pause the video, spend some time and work through this example before I walk through it with you. See if you can solve this on your own. Okay? Find the volume with the appropriate uncertainty as an absolute uncertainty. Okay? So I give you the radius and I give you the height, and the radius and the height both have uncertainties associated with them. So we got to figure out how this goes through in the calculation. Okay, so just be patient as I walk you through this. Okay, and pause the video and review any step that you need to at your leisure. Okay, all right. So first of all, the volume of the cylinder is given by the area times the height. I get 92.5 cubic centimeters. Now, because I'm multiplying data together, I'm going to have to deal with some percent uncertainties. And I also have data raised to a power, so I know I'm definitely going to deal with a percent uncertainty, okay? First, the percent uncertainty in R, okay, is going to be the uncertainty, which is 0.01, divided by the actual value times 100, and that's 0.625. And I'm going to leave that as 0.00625, okay? So even though I multiply it by 100, I leave it as this, and you'll see the value, the wisdom in doing that in just a minute. The percent uncertainty in R squared is going to be 2 times that, right? 0.01250, I'm leaving it as a decimal. And the percent uncertainty in H, I'm going to leave as 0.00870, okay? So the percentage uncertainty in the volume is going to be what? Well, it's going to be the percent uncertainty in R squared plus the percent uncertainty in H, because that's what's given in this equation. Remember, pi doesn't have any uncertainty associated with it. It's just basically a counting number or a constant, okay? So if you add those two together, you get 0.02120. So the absolute uncertainty, now you got to go backwards again, okay? So it's 0.02120 times the actual value of the volume that I calculated way back here. And here I'm using more significant figures than I know I'm going to use, because I want the final value to be as accurate as possible, okay? You see why I kept it as a full decimal? Because I'm going to multiply this by the actual volume anyway to get the final absolute uncertainty. Had I multiplied it by 100 and kept it as 0.625, I would have to then divide this by 100 anyway. So why not just leave it as 0.02120 and 0.00625 and so forth? So the final answer with sig figs is therefore 92.5 plus or minus 2, where I'm using one non-zero digit in my uncertainty. Okay, so again, pause this, go back, rewind it. Make sure that you understand what I'm doing here, because this is super important. It's your first real example of doing all this stuff. Okay? Okay, another example, past paper 1 question. Go ahead and try this one. So the power dissipated in the is equal to I squared R. Interesting. Okay? Now you guys haven't learned this yet, but the power dissipated in a resistor of resistance R carrying a current is equal to I squared R. The value of I has an uncertainty of plus or minus 2%. The value of R has an uncertainty of 10%. What's the value of the uncertainty in the calculated power dissipation? Well, okay, it's going to be 14%, obviously, and here's because you multiply, because you're squaring I, you multiply its uncertainty, its percent uncertainty by 2, so you get 14% according to our rules. Try this example, example 10. Another great past paper question from paper 1, okay? Student measures two lengths as follows, all right? The student calculates all these different things, okay? Which of these uncertainties has the largest magnitude? Well, okay, the percent uncertainty is in T, and remember, you're doing this without a calculator, I should remind you, okay? Percent uncertainty is T is 0.01, that's 1%. Percent uncertainty in S is 0.5%. T minus S, T plus S, okay? All right? Okay, this one is going to be the smallest, all right? Okay, so the answer would be C, which is F of T minus S, okay? All right. Okay. Oh, by the way, I should actually mention this. The largest magnitude, right? The largest magnitude. That's very important here. So make sure that you understand my answer to example 10. Okay? All right, example 11. Go ahead and pause the video and read it. Okay, so I have a volume of height h and radius r given by the expression da-da-da. In a particular experiment, r is to be determined from measurements of v and h. Interesting. The uncertainties in v and h are V is plus or minus 7%, H plus or minus 3%. What's the approximate uncertainty in R? Okay, what are you going to do here? Well, this is interesting. You're going to have to solve this equation for R first. Remember, this is a paper 1 question, meaning you can't use a calculator. So R is V over pi H to the 1/2. So the uncertainty in R would be 1/2, okay, because your power is 1/2. The percent uncertainty in V plus the percent uncertainty in H, because you're dividing V by H, okay? So it's going to be 1/2 of 7 plus 3, which is 5%, okay? So the answer is B. Really great question. Paper 1 question, no calculator, okay? All right, so I'm going to blow through this one really quick, the max and min lines, because we've already covered this in class. You can use graphs to express and find uncertainties, all right? And we do this all the time. In fact, you're required to do it in the IB. You must include graphs of your data in aspect 3 of DCP, and you know what I'm talking about if you've checked out the lab rubric, okay? Let's say you've gotten to the point where you've taken data, decided which variables to graph on the x and y axes. You've done so with the proper error bars, and you found the line of best fit and the slope of this line. Usually you'd use graphical analysis or log or pro or something like that. Therefore, you found a value of the slope that corresponds to some physical quantity. You must now use the max and min best fit lines to determine your final uncertainty and your stated value of the slope of your best fit line, okay? Now, we've done it before, that's why I'm going fast. Here's how. You draw a straight line with the least slope possible that fits the top and bottom corners of most of your error boxes by eye, okay? And there's a way to do that in Logger Pro that I've already shown you guys how to do that. It's by eye. It's your estimation. We might get different answers. If there's 12 of us, we might get 12 different answers with the same data, okay? Because it's your estimation by eye. You determine the straight line with the greatest slope possible that fits the top and bottom corners of most of your data, most of your error boxes, okay? And then you determine the slopes of these two lines. The final uncertainty in the stated value of your slope, which is an experimental quantity, is the max slope minus the min slope divided by 2. So you can see in these two cases, we've drawn the steepest gradient and the shallowest gradient that fits generally most of the error boxes, okay? And it's okay for max and min lines to not go through every single error box, okay? So example 12, go ahead and try this one, okay? The quantity given by the gradient of the graph is going to be 1/2 of A, okay? Because distance is 1/2 acceleration times time squared. Now, you haven't really learned that yet, so I'm kind of telling you that, but the gradient is half the acceleration of this object. Explain why the graph suggests that collected data is valid but includes the systematic error, because it doesn't go through the origin. Here's the systematic error, is this offset right here. Does the data suggest that distance is proportional to time? No. It's linear, but it doesn't pass through the origin. Okay? Continue. Making allowance for the systematic error, calculate the acceleration of the object. Okay? All right? The acceleration is 1/2 A. So you find the slope. You find the slope however you want. Use the most data possible. In this case, I got 36 centimeters per second squared. Okay, this graph shows the same data after the uncertainty ranges have been calculated and drawn as error bars. Okay, so the IB is giving you the actual error bars. Draw the best fit line and add 2 more lines to show the range of the possible acceptable values for the grading of the graph. Classic IB question. Okay, here's my best fit line. I'm using tons of my data, as much of my data as possible. Okay, and usually what I do is my max line I make it red, and my min line I make it blue. Okay, I don't always make my my best fit line green, but that's actually a pretty good idea. Usually I make it black. But green's pretty good, so I like colors because colors immediately show you, immediately differentiate between what you're looking at. So that's what we're looking at here.